Okay. Okay. So I'm glad everybody is here. So I wanted to thank Midge for the invitation as well as for years of collaboration. This is joint work with her as well as with Jim. And so I apologize if the level seems a little bit basic at the beginning. This is deliberate. It's not because of the level of mathematics I think you understand. It's trying to use as little mathematics as possible. So depending on whatever students you have in the room, you will be able to communicate with them about problems like this. So it's what is the least amount of mathematics we need to get to a certain point. As a pure mathematician, I often have to really remind myself not to go for the biggest possible general theory and say, we don't need to develop all of this. In fact, all we need is this little snippet here, and we can take this beautiful path. And yes, there's a lot of wonderful things that we're walking right by, but keeping the focus on cryptography, what do we need to get to the student to get the student to the point where they can understand what's going on, where they can be motivated to learn more mathematics, and they might even be prepared to do some original research. So the final lecture is work that Jim and I were doing recently about trying to do error detecting, error correcting codes, where I will pose some problems which may or may not be open. I'm working on some of them with high school students right now. They're just great ways to introduce people to the ideas of research. How do you ask a good question? How do you start gathering data? How do you then convert that to something more meaningful? And so I am happy to try to go into more detail if people want to know more theory. I will say as a disclaimer, I am one of the few mathematicians you will meet who is tenured and has never taken a course in group theory or abstract algebra. I've taught it, don't worry, I've taught it, but I've never actually taken a math class in group theory or abstract algebra. There's a reason why. It was an interesting path I took when I was younger.
And he's a number theorist, so.
Okay, so really make it look bad, yes. I am a number theorist, but I'm an analytic number theorist, not an algebraic number theorist. So it's socially acceptable. So what I want to do today is I want to start off with the first bit about talking about alphabet codes. And so I realize a lot of you have probably seen much of this before, but I want to try to talk about what do we need to really present it to students who have not done much mathematics or may even be afraid of some of mathematics. And how can we use this to explain some good math concepts? So a lot of this is based on lectures I've been given recently to high school students, actually to some elementary school students, to make sure I got elementary school students who were motivated to do mathematics, because we had 60 kids in grades 4 to 6 in my elementary school who were doing math club out of a population of about 450. Well, this is being recorded, so I will not conjecture why the students are there. I will say that when you write in the description for the math enrichment that there will be homework assignments, it's amazing how few people sign up. And so the people I got all wanted to be there, which was wonderful. And I'm sure my kids wanted to be there. All right, so I'm going to talk about the Caesar and Athlean ciphers first. Out of curiosity, how many of you have seen the Caesar cipher before? Okay, good number. Okay, so the idea is we want to create a function that will map us from the alphabet to the alphabet. And so you give me a letter and I'm going to tell you what it encrypts to, and then you should be able to have a way to tell me what it decrypts back to. If I can encrypt a message, if you can't decrypt the message, it's not really useful. Later on, we might talk about efficiency. If it takes 10 years to encrypt a message, okay, it might be secure, but it's not really going to be that practical. Similarly for decryption, there are times when we need to encrypt and decrypt very quickly. If you're in a battlefield situation, you need to be able to decrypt the message very quickly. In terms of the security of the message, in a battlefield situation, the message doesn't have to be that secure. If it will take the enemy 3 or 4 hours to crack your message, that's fine. The battlefield conditions will change up. It's like, change the guns and point the guns here. That message doesn't have to be secure for that long. If instead it's something like D-Day, where this is an operation that's being planned over several months, you need more security than just a couple of hours. So the first thing we want to make sure is that the following 2 conditions hold. Different letters go to different letters, and all letters are hit. Now, as a mathematician, we always talk about, well, what is the minimum set of conditions we need? Do we really need both of these conditions? So I see one person shaking their head or looking at the beautiful weather outside. I can't quite tell which. So do we need both conditions, or is one condition enough to imply the other?
Don't you need also for the commas and the full stop?
So you could, so then the definition is, what do you consider a letter? So you might want to say instead of a letter, maybe we'll do characters, and every character goes to a character, and different characters go to different characters. So you don't have collisions. We don't want A and B both to be sent to the letter Q.
So one-to-one correspondence.
A one-to-one correspondence. So do I need both conditions?
Yes.
Does one condition imply the other?
Yes. Yeah, it's onto functions, right? It's one-to-one and onto.
It's one-to-one and onto. So if different letters go to different letters, let's say I have 26 letters.
Yeah.
Is it, if every letter goes to a different letter than every other, can two things go to the same letter? No.
No.
So is every letter hit? Yes. And the reason is it's a finite alphabet. You know, if we had an infinite alphabet, it would be very different. So I could take the natural numbers, and I could have the function that sends each number to its successor. So n goes to n plus 1. In that case, different letters will go to different letters, but not everything will be hit. So because things are finite, we're in great shape. Out of curiosity, has anybody ever stayed at the Hilbert Hotel or heard of the Hilbert Hotel?
Course, yeah.
Is anybody here who's not heard of the Hilbert Hotel? Okay, this is a wonderful hotel. Sadly, they were booked this weekend. Although actually, it doesn't matter at the Hilbert Hotel if they're booked. So this is a hotel that can always accommodate more guests, even if every room is filled. So you have infinitely many rooms, and a guest arrives, and it's Midge. We don't want to have her, sitting out in the rain or the ice storms or whatever's going on. So what they do is they bump everybody to the next room. So person 1 goes to room 2, person 2 goes to room 3, and that opens up a new spot. So you can always accommodate a new guest. You can accommodate finitely many new guests. In fact, you can accommodate infinitely many new guests. Send person 1 to room 2, person 2 to room 4, person 3 to room 6. You just send everybody to their double room, and you freed up infinitely many rooms. So this becomes a nice way to talk to students about the differences between finite and infinite and some nice subtleties. Okay, so the setup, bless you, is let's let x be our input letter, and then f of x will be the encrypted letter. And we'll need, of course, a way to decrypt at the end of the day. So we can't use the function f of x equals c. So I always like to talk to my students, well, what's the easiest thing we could try? Well, the easiest thing is the constant function. Well, if we send every letter to c, it's going to be a very interesting message to try to decrypt. So we need something a little bit more complicated. So what's the next most complicated function you can look at? And so even at the level of algebra 1, this is a way to start introducing what do functions look like? What can we use them for? And so let's try f of x as, a multi, x plus c. And then of course, later on, we'll put in some number in front of the x, but let's just keep it simple, just x plus some c. So the standard one is c equals 3. And so this was Caesar's cipher to encrypt messages. One of my favorite quotes about the Caesar cipher was back then so few people could read, just writing down the message was almost enough to encrypt it. But we'll shift every letter by 3. So A goes to D, B goes to E, et cetera, et cetera, et cetera. W goes to Z, and then things get interesting. Well, if we shift the letter X, what does it go to? Well, natural thing to say is just wrap things around, and X will go to A, Y to B, Z to C. So this is clock arithmetic. If it's 10 o'clock now, what time is it in 5 hours? 10 plus 5 is 3. You could also say 15, and we could have a military time, but this is a much more casual gathering. So we'll say 10 plus 5 is 3. So we'll say two numbers are the same if they differ by a multiple of 12. And so for the alphabet, we'll say two numbers are the same if they differ by a multiple of 26. So how would we decrypt?
Going back.
Yeah, just go back 3.
Inverse function.
Inverse function. So we would just use, g of y is y minus c. So it's very nice to go back and forth between the two. So here is just writing everything linearly, going from A to Z, or I think a better way of looking at it is just writing it on a wheel and just seeing how it just wraps around like this. So is the Caesar cipher a good cipher to use? No, why not?
Easy to decrypt.
It is extremely easy to decrypt. How many things do you have to try to decrypt it? There's a split in the community as to how many things there are to try. There are two different answers. So how many things are there to try to decrypt the Caesar cipher? 25, or what's the other possible answer? 26. It is possible that you could choose a shift of 26, which of course has no effective encryption.
But certain things repeat, so you can quickly find it, like 2 and A and da.
Well, this is if you try to choose like letter frequency,
Yeah.
which we'll talk about later. But I'm saying for the Caesar cipher, there's only 25 or 26 choices. What do you want to shift A to? I've got to move A to another letter of the alphabet. Here I chose to move A to D. I have 26 choices. It seems a little foolish to choose to move A to A, B to B, C to C. It's not really going to be that much level of security. For encryption, you want to make sure that only the intended recipient can read it, not just any recipient. But when you're trying to do the analysis, it's sometimes easier to include the one bad encryption choice just because it makes calculating how many things are easier, so you don't have to worry about, well, if I choose this and this and this and this and this, that turns out to be a bad case, and then just keeping track of what that is. Okay.
This is a great illustration for Latin alphabet, phonetic.
Yes.
Alphabet. Many languages on the earth, including Chinese language, Japanese, and so on, they are of different origin. And it's not so easy to apply this type of clock arithmetic.
Yes, and in fact, one of my colleagues, Tom Gowdy, was giving a talk yesterday at Williams to the general science summer students. And he was talking about continued fractions, but first he was talking about how you can represent numbers, and he was representing numbers in Roman numerals. And he wrote a multiplication problem in Roman numerals. And as expected, everybody cringed at the thought of trying to do multiplication in Roman numerals. And the first thing you do when you have something like that is, well, okay, if you're going to make me do this, I'm going to convert the Roman numerals to regular numbers, multiply them, and then I'll convert back. And so you could, of course, use the Caesar cipher directly with the letters, but I think it's easier to first just take the letters. So this is the great message meet at 10 to indicate the start of this talk. And you can write the letters as their numerical value. And then it's just a lot easier to just do the adding 3 and then to decrypt subtracting 3. One of the nice things is if we replace replace letters with numbers, we now have the ability to do mathematical operations on them. This is why if you teach probability and you talk about flipping a coin, we don't really want to record things as heads and tails. We might want to record things as a 1 or a 0 or a 1 or a -1, because then we can say, well, what is 2 heads plus a tail? Is we can do operations like that. So there's a lot of great little sides that you can get into when you are talking to students with stuff like this. All right. So we all agree that the Caesar cipher sucks. It is almost no level of security. You can crack it very quickly. So let's baby steps. Let's try to make it a little bit more complicated. So the next thing we could try is the linear function. F of x is ax plus b, where now we allow some choice of a. Of course, we could take a equals 1. That's perfectly fine. And then the question is, which choices of a will lead to a valid encryption decryption scheme? It might not be the case that they all work. For the value of b, any choice worked. So which b's are possible? Well, any b is possible. All b does is just translate everything. It just shifts everything down. B is not a big deal. The meat of the action is what's going on with a, the slope. Just how much, when one step in x, if I change my input letter by one number, how much do I choose? How much do I change the output number by? So that slope is what's going to be really important. So in the interest of space, rather than working with the 26-letter alphabet due to budget cuts, we will only have a 6-letter alphabet. I don't think you can do any bad 4-letter words with this, but I'm sure somebody will prove me wrong before this talk is done. So the alphabet is now A, B, C, D, E, F. And so we'll have A, B1, B, B2, all the way up to F, B6. And then the question is, all B work, which A work? So since all B does is just translate everything and it just spins the wheel when we're done, we can actually break this up into 2 different operations. You first multiply your input number by A, and then you shift by B. So this is a great way to talk about breaking up a complicated problem into a simpler problem. And so I'll tell my students, well, look, we've already handled the Caesar shift, that's just the B. So now let's just focus on B equals 0, because we understand how to do that, and see which A work. So the first A to do is hope this is readable, is we'll take A equals 1. So here's my letters A, B, C, D, E, F, and I add 1 to keep marching down in the first row. And then what letter does it correspond to? Well, if A equals 1, every time I increase my input letter by 1 number, I change the bottom one by 1. So it's going to just be C, D, E, F, A, B. And you see basically that this is just, so actually I guess this is not B equals 0. What am I taking B to be? 1. No, I think 2. So this is b equals 2, not b equals 0. So I apologize, there was a typo there. So I can write on this screen though, right? This erases.
Yes.
Yeah. So at least on this one I can fix it. I see stuff has been written over here, but I think that's probably not a good idea. All right, so everything works fine with a equals 1, which is not surprising. Now let's take a equals 2. And so I'm going to still start off by sending A to C, but now every time I increase my letter by 1 upstairs, I increase by 2 downstairs. So I would go from C to E to A to C to E to A. And you can see that if I'm only increasing by steps of 2 every single time, I'm not going to hit every letter. I'm going to only hit half of them. And you can do this for all the different choices of A. So we've already done A equals 1, we've done A equals 2, and that's going to fail because we just get basically 2, 4, 6, 2, 4, 6. Well, we know that since 2 fails, we can be lazy. There's no need to look at 4 because 4 is just basically 2, 2. You can do 4 again by brute force if you want. 6 will also fail. There's no need to do 6 directly. We can.
In their case, you also have enough to study A and take B equal to 2.
Right, so I accidentally had B equals 2 in the picture. I should really have B equals 0, so we start off with A going to A. I unfortunately drew the picture with B equals 2, not B equals 0.
So we do have B equal to 0.
And what's pictured over here, we have an initial shift of B equals 2. If I take A equals 3, so if I start off with the number 1.
Back to the previous slide,
Yep.
because I don't understand the shifts. What is the value for A and what is the value for B?
Here,
First one, A plus 1 is.
So it's the letter right after A. So if I add 1 to A, I would get B. If I add 1 to B, I would get C. If I add 1 to C, I get D.
So for this one, you have A equal 1 and B equal 1.
Not A equals 1. I'm saying if I take the letter A, I'm just marching down on the top. I'm just adding, next letter, next letter, next letter. And then I'm starting down here and I'm saying what would happen is I shift things. So let's,
So the second is, yeah, the second, because the second row should be A equal to 2. And
so let's just do a new one right here. So let's take f of x equals x. Right, so let's just do f of x equals x. So if I do it that way, f of 1 is 1, f of 2 is 2, f of 3 is 3, and so on, so on, so on. So you see A goes to A, B goes to B. Now let's take f of x equals 2x. Then f of 1 is equal to 2, f of 2 is equal to 4, f of 3, f of 3 equals 6, f of 4 is 8, but since we're looking at a clock with 6 hours, it's going to just be 2. And then f of 5 is going to be 10, which is the same as 4. And then f of 6 is going to be 12, which is the same as 6. So in this case, we now have A goes to B. We have B goes to D. We have C goes to F. And then we have D goes to B. And then we have,
so it's not 1 to 1.
it's not 1 to 1. So E goes to D. And finally, we have F goes to F.
Yeah, no,
F of 6 is 6. So
this is not going to work.
So this will not work. So we notice we get D twice. We have E, so we have, let's see, so we have A and D go to B. We have B and E go to D. And we have C and F go to F. So this fails. So A equals 2 is bad.
It's because of these sets. It's not integral domain. That's the reason. That's abstract algebra, sorry.
Well, but the question is, are there some choices that would work? And so,
Prime numbers will work.
but I'm saying if we try A equals 3 will fail. So A would go, 1 goes to 3, 2 goes to 6, 3 goes to 9, which is the same as 3. So if we try A equals 3, it's going to fail. Ah, so I heard relatively prime. If we try A equals 5, A equals 5 actually works.
Right.
So the question is, even though there are some issues with 6, 6 has some factors, there are still some valid choices for A. So it's not that everything is bad. It's some things are bad. And then this becomes an opportunity to ask students, what do you think is going to work? And can you figure out, why does 1 and 5 work? What's special about 1 and 5 that is not special about, or not good about 2, 3, and 4, and 6 in this problem?
Yeah.
And then of course what they should do is, well, after you've done this great analysis of 6, look at other numbers and get a table and try to see the pattern. And so the more times you can have students actually doing things, it takes time, but then they can actually build that sense of discovery. And so as has been remarked already, the pattern is 1 and 5 do not have a common divisor with 6, other than, of course, the trivial 1, and we never let that bother us. So there's no non-trivial divisor for 1 and 5 and 6. But 2, 3, 4, and 6 all have a common divisor. 2, 4, 6, they all share 2, 3, and 6 also share 3. Okay, so it's the A that work that are relatively prime. So what do you think will work for a 26-letter alphabet? How many numbers do you think we can choose for A that will be valid? So anybody know what the answer would be?
The Euler function.
The Euler function. And so how many would it be?
I don't have it memorized, but you can figure it out.
So can somebody tell me numbers that won't work? Let's go the other way. Which numbers are bad?
2.
Even numbers. So we've already thrown away half of the possible numbers.
Exactly.
So now we're only left with the odd numbers.
Yeah.
Which odd numbers share a factor with 26?
13.
13. Anything else? Multiples of 13. So it's 13 and 26.
Yep.
So sometimes it's easier to look at the opposite problem.
Yep.
If I can figure out the probability of failure, well, the probability of success should hopefully be 1 minus. As long as there's no ties. So a lot of times it's easy to compute the complementary probability. So for this one, let's just list easily the numbers that fail. It's got to be numbers that have common factors with 26. So we lose 13 even numbers.
Right. So,
And we lose, what, did I make a mistake?
We lose an infinite number of even numbers.
So I am going to be very restrictive here, and I will only consider numbers from 1 to 26.
Yeah.
So of the 26 numbers, we want to keep the problem finite. Mitch has told me I only have a certain amount of time to speak.
so we
But if people want to stay longer,
we already lost 13 of them.
so we lost 13 of them.
And then we also lost 13, so we lost 14 of them.
Correct, so we've lost 14. So how many numbers work?
Okay. So 26 minus
26 minus 14, which is 12.
Yep.
Now we actually lost 2 numbers for 13. We lost 13 and we lost 26. But we've already removed 26. We're not going to remove it twice. So the answer is 12 choices. So the Caesar cipher, we have 26 choices.
So that's the Euler number.
So that's the Euler number. And we will actually get to the Euler number very soon, or the Euler Totient function. So the Caesar cipher has 26 choices that work. The Athlean cipher, AX plus B, where we have a choice for A and a choice for B, we will have 312 possibilities that work. That looks a bit better. It's more than a factor of 10 more. Are you comfortable with the level of security with 312 codes? No. What if I told you that you are not allowed to use your computers or phones, that you have to do this by hand? Are you comfortable with the level of security?
Then we have to.
Well, how many people do we have here? So we've got what, on the order of 20? So we divide 312 among 20 people. So each one has to do what, around 15 codes and checks?
Can we use a calculator?
No. Your electromagnetic pulse has been detonated. Terrorists have decided that they must destroy all future math education. And they've realized that this is the key target. So no electronic devices work. Could we check, do you think you could check 15 possibilities in an hour?
No. Yeah, I could.
Yeah, this isn't that bad. So your hour is 60 minutes, it's 4 minutes to try. All you have to do is start trying to decrypt the message. And if the begin, okay, that's probably not it. Let me move on to the next one. And depending on how you're checking things, it's a very easy way to, okay, if I'm going to move from this one to the next pair AB, I know how to take what I already have and just shift it over a little bit more. So it's a nice exercise. Try to come up with a good methodical way to minimize your computations to try all the different codes. So what I might want to do is I might want to fix A and then try a couple of different B's, because all the B's will do is just change the shift by 1 and see how is that working. So you can check a lot of things very quickly. I would be shocked if it would take us an hour as a group to do this. I have no desire to see how quickly we could do this as a group. But if you have some students, it might be an interesting exercise. How fast can you do it? Break the students up into different teams, see which team can do it the fastest. I did some stuff like this with my students. I'm saying, one of the things, if anybody can solve this, free movie night. So 312 is not good for security. So we tried the constant function, sucked. Tried a linear function, ax plus b, was a little bit better, but it's still not a great level of security. What if we tried a higher degree polynomial? What if we tried a quadratic? Students love learning the quadratic formula and doing problem after problem after problem of finding the roots. And you can actually use the quadratic function to build a different type of encryption, which if people are interested in, I'm happy to talk about how you can use the quadratic polynomials to do encryption. Do you think we could use a quadratic function here rather than a linear function? And if so, then maybe we would have 3 coefficients, and maybe we'd have more choices. And then to get even more security, we could go up to a cubic, a quartic, a quintic. So what do you think? Do you think a quadratic function will work, or do you think there might be issues with a quadratic function?
I think there are issues.
So what do you think the issues are?
We will find out. No,
Well, I'm asking.
it will map to more than one.
So we have the possibility of repeated roots of things being mapped to the same thing. So as a really nice exercise, you can then show that if we tried to do quadratic, there would be issues. So I will leave that as a fun exercise, or at least as an exercise. And it has been remarked by some, there is a lot of math lurking in the background. And so one of the big things that's lurking in the background is the Euler Totient function. If you ever hear the name Euler or Gauss, it's probably important, it's probably worthwhile to look at. And it's a great way to find very easily the answer to the question we want. How many numbers are relatively prime to a given number? So we've already seen that the numbers that are relatively prime have some very important properties, and they're very valuable for building up certain types of codes and problems. So what we're going to do is we're going to just have as a definition, phi of n is the number of numbers from 1 to n that are relatively prime to n. So we will consider 1 is relatively prime to everything. You need to have a non-trivial divisor. So that's why 4 and 26, that will not be considered relatively prime, but 1 and 26 will. So what do you think the easiest number to calculate is for phi? What value of n? Should be one value that strikes you as immediately. This is the value that's easiest to compute. Nope. Because that's infinitely many values. Phi of? No, but what's the easiest choice of n? Yes, and thank you for using that finger. The number 1. Right? Start in the beginning. Phi of 1. Okay, let's look at all the numbers from 1 to 1 that don't share any non-trivial factors with 1. That's just 1. Phi of 1 is 1. Then
1 as a prime number.
I never said it's prime. I just said, what is the easiest n to look at? I didn't write that on the board. I just asked, what's the easiest n to look at? So the easiest n to look at is n equals 1. Then, yes?
It's computer science. Can you please remind us what is a relatively prime number?
Sure.
In opposition to prime number.
Oh, but it doesn't race.
Like 3 and 5 is relatively prime.
Okay, so
they don't have common divisor.
So x and y are relatively prime if the only number dividing both is 1. So with this definition, 1 will be considered relatively prime to everything else. So we sometimes talk about a non-trivial common divisor.
Yeah.
And so 1 is a trivial common divisor, so we don't really want to consider that, because then every pair of numbers will have a common divisor. And so it's not going to be a good definition for us. Okay, so the next thing, you're welcome. The next thing which was remarked is there are certain numbers that are going to be very easy to compute. And while we are using this right now to get a sense of how many possibilities we have for the Athlean cipher, later today when we get to the RSA encryption scheme, this is going to be extremely important. So if P is a prime number, so a number is prime if its only divisors are 1 in itself and it is at least 2. Or another way of saying it is you have to have exactly 2 distinct divisors, 1 in itself. We do not want 1 to be considered prime. The reason is if 1 is considered prime, you lose unique factorization. So every number can be written uniquely as a product of prime powers if you write the numbers in increasing, you write the primes in increasing order. If you allow 1 to be prime, then I could multiply it by factorization by 1 to the 2019 or 1 to the 1776, and it would still be a valid factorization. So 1 is considered special, 1 is considered a unit. So if phi is prime, how many numbers are there from 1 to p that are relatively prime to p? It'll be p minus 1. And so the numbers that work is 1 works, 2 works, 3 works, 4 works, all the way up to p minus 1, because since p is prime, the only things that divide p are 1 in itself, so it can't have any common factors with numbers less than it other than 1. Okay, so that was pretty good. What if we take p squared? How many numbers are relatively prime to p squared from 1 to p? P is still prime. So one of the habits you learn in number theory is p should never be used except for prime numbers unless you absolutely have to. If you're in another subject like probability, then p will be a probability. If you're in analysis, it could be an LP space. But for us, p will always be prime, n will be a general integer, which sometimes might want to be prime, and sometimes we'll have to say, I'm sorry, you're not. So how many numbers would be relatively prime to p squared? So p prime, let's look at phi of p squared. So we have the numbers 1, 2, 3, all the way up to p squared. So how many numbers do you think are going to be relatively prime to p squared? So for a lot of problems like this, instead of asking which numbers are relatively prime to p squared, ask the inverse question. Ask the dual question. What's the dual question? Which numbers share a factor? So ask which numbers share a factor with p squared and subtract that from p squared, or subtract that number. So if I can easily figure out how many numbers share a factor with p squared, these are the ones that are not relatively prime. And I'll just subtract that from p squared. So which numbers share a factor? Okay, good. Sharing factor, we have p, 2p, 3p, all the way up to what? All the way up to p squared. So yes, because how many? P share a factor. So phi of p squared will be p squared minus p. And if you want, you can write it either way. I prefer to write it as p squared minus p because that's reminding me how this calculation was done. I had p squared numbers and I'm throwing away p numbers that share a factor. Okay. Lose p, 2p, etc. And there should be a parenthesis there as well. If n is p cubed, how many numbers will I lose? I'll lose p squared. And so I'll get p cubed minus p squared. So in general, if I had p to the 5th, it would be p to the 5th minus p to the 4th. It turns out that the Euler-Totient function is multiplicative. We do not need that for the goals today, but since there are some people in the audience who do know abstract algebra, I will just say things like that. We only need for cryptography the value of phi at primes and the value of phi at the product of 2 distinct primes. So I actually don't need p squared, I don't need p cubed. I could resist, but I chose not to, just because it's good to do some of these calculations, but we won't do the general case. As a wonderful exercise, you want to prove if you take 2 numbers that are relatively prime, So M and N relatively prime. So phi of Mn is phi of M times phi of N. And what's nice about this is it allows you to calculate the totient function of a compound number in terms of the totient function of simpler ones. And then what you do for each one of these is you just take M to be all the powers of 2, say, that divide. And no powers of 2, all the powers of 3. And you can break it up into understanding what's going on at the primes. So if you know a number's prime factorization, you can figure out the number of numbers relatively prime to it. We don't need that, but it's a nice exercise. And for people who want to go further, it's something you can talk about. What we will need is if P and Q are distinct primes, then how many numbers are relatively prime to phi of PQ? So I'll toggle back to the writing screen. P and Q distinct primes. What is phi of PQ? Okay, so how did you get P minus 1, Q minus 1?
That is phi of
Well, okay, so it is P minus 1, Q minus 1 if you prove it's multiplicative. So one way to calculate this value is you first prove that the function is multiplicative, you know its value at primes, and then you're done. But that requires you to prove the multiplicativity. And that's even a hard word for me to say as a Bostonian. At least it doesn't have any R's. But can we prove it more elementarily without going into all the deep properties of the totient function? All I want to do is the least amount of mathematics possible to get that phi of PQ is equal to P minus 1, Q minus 1. And in fact, for the proof, it's actually better not to write it as P minus 1, Q minus 1. So let's actually take this as a conjecture. Yeah, so let's conjecture that it's P minus 1 times Q minus 1. And we got that from doing a lot of small examples by hand, seeing what the answers were. We get, always looks like it's P minus 1, Q minus 1. And we'll expand this out, and we get PQ minus P minus Q plus 1. And so the question is, when you look at it like this, does that suggest anything? So much of mathematics is finding a way to interpret the algebra that you're looking at. And if you can tell the right story, you're in great shape. So what does the PQ remind us of? Yeah, how many numbers we have total? So it's the total number minus, how should we view the P?
one of the factors.
It is one of the factors. It's the multiples of Q that are bad. How many multiples of Q are bad? There's Q, 2Q, 3Q with the Boston accent. I'm going to stop there. Yeah, I know, Jim.
I promised not to ask you what comes after 3Q.
5Q comes after. It just doesn't come immediately after. So as a Bostonian, I will stop at 3Q. You can try to figure out what that would sound like in my accent. So then you go all the way up to P times Q. So you lose P multiples of Q. So we subtract off P multiples of Q. Then we subtract off Q multiples of P. And then we add 1. Why do we add 1? The overlap. Subtracted PQ twice. So we removed PQ once as a multiple of Q and once as a multiple of P. We can't remove it twice. It was on the list once, you can't remove it twice. So we have to add it back. So now it will not be on the list at all. It's included here and here, it's removed here and here. So this is the advantage of, if you can have a conjectured formula, it can guide how you do the proof. It suggests that here's a great way to do the counting. And so if I toggle back, this is just explicitly writing down. We lose P multiples of Q, we lose Q multiples of P, double counting PQ, so we add it back, and there is our formula. And again, as an exercise, try to prove that phi is multiplicative. See if you can push this proof forward. But it's not needed. Fortunately for RSA, we just need to deal with the product of two distinct primes. Okay, so the next is to try to come up with a better method of encryption. So I don't want to go into too much detail about all of these. I want to basically just give you a sense of the landscape. These encryption schemes are for the most part not used, or they're not used as the primary way. Is we might use one of them, but use a more secure way to generate the secret key to feed into them. The advantage of the alphabet ciphers like this is they're extremely fast and easy to use. Later for RSA, if people are interested, I actually wrote some code to implement it in Mathematica to actually work with taking a 400-digit number and raising it to a 400-digit number. If you have a standard calculator, sometimes when people play geek games, they see what's the largest factorial they can take before the calculator overflows. You know, how big of a number can you work before the calculator says, I'm done? Mm-hmm. And so to take a 400-digit number and raise it to a 400-digit number is overwhelming. If you don't find a fast way to do it, theoretically, yes, it's a great way to encrypt things, but practically the universe will be dead. And we'll actually quantify just how dead the universe will be. So here's one possibility. A big defect of the Caesar cipher and the Athlean cipher is they always send the same letter to the same letter. So we'll talk in a few minutes about frequency analysis. I've heard some people, mumbling that already. If you look at the daily cryptograms in newspapers, these are very easy to solve. Now, one of the reasons they're easy to solve is they're kind and they include spaces. If I was going to send a message, I would not include spaces. I would also deliberately misspell some words. But when you have spaces, if you ever see in English a one-letter word, assuming the person can spell, it's either I or A, unless there was a mistransmission. We'll talk about that in the last lecture. So you have a big clue. So the Venire cipher works as follows. You take a message, Dad can add a bed. Okay? Anybody know why I chose the sentence, Dad can add a bed? Yeah, I'm basically trying to keep working with just a 6-letter alphabet. It is very hard to write at the level of Shakespeare with a 6-letter alphabet. He has a cast of thousands in what he writes. All right, well, it's 26. So I chose as my key phrase ABC, ABC, ABC. So I just keep writing ABC, ABC, ABC under. And what I do is I shift the first letter by A. So I shift it down by 1. So D goes to E. A has a B underneath it, so I shift A by 2, so A goes to C. D has a C underneath it, so I shift it by 3, so it goes to G. So at this point, I will allow myself a 26-letter alphabet. I'm just writing that to just have a little fun. What's nice is we see already that the letter D has been encrypted to an E and to a G. So if you try to do a frequency analysis, it's going to be a little bit harder. It turns out that there are still ways to crack this. I don't want to go into too much of the detail. I'm going to just list. Yes.
Question.
Yes.
Why do you have a Q if it's only 6-letter alphabet?
Well, I said I was just writing the message in a 6-letter alphabet. I'm still using the 26-letter alphabet. If I wanted to, I could keep everything in the 6, but I wanted to show you that, you have collision very quickly.
Oh, right.
So the same letter is sent to 2 different things. So both D's, the 2 D's go to an E and a G, but also notice that, let's see. If I take C, A went to C, that A went to C. If I have, what else do I have? I have a D, so C went to D and B went to D. So 2 different letters went to the same letter and the same letter went to 2 different letters. So this is very different than the other codes we were looking at. Yes?
So is this analogous to hashing in computer science where you are, when you have things go into other things, you get collisions and all that? You know what I'm talking about hashing?
Right.
Yeah.
No.
I don't think it's quite the same.
Isn't a hash function in some ways could be like one of these cryptographic functions?
So for the hash function,
You allow collisions there.
What?
You allow collisions there.
Right, you do. But
Right.
That's what I'm saying.
for the hash function, you're trying to have collisions be rare.
That's right. That's right.
And so here the whole point is you want this to be happening. So that if somebody tries to do a frequency analysis, there's going to be some issues. It turns out that the way to solve this is, imagine you don't know the key phrase, but you know its length. So if you know its length is 3, you split the message into 3s. Everything in a spot 1 mod 3, everything in a spot 2 mod 3, everything in a spot 3 mod 3. And then your message would have 3 different sub-messages. And in each one of them, the letters would be sent to the same thing. So you would have 3 examples of the Caesar cipher. And then for each one of them, you would do a frequency analysis. And it turns out that there are ways to figure out what the length of the key phrase is. And so the last link over that here gives you some clues on that. There's a wonderful story about how secure is the Venire cipher. So a couple of years ago, someone actually found a message encrypted in the Venire cipher outside of Vicksburg. It was a message from the Civil War. And it had been thrown in the river. And there were a lot of wonderful stories about it. Now, with 21st century computers, it's not very hard to break Civil War Venire encryptions. But a lot of mathematicians, oh, let's just see if we can break it by, for fun, just by hand. A lot of times people make mistakes in messages. If you always begin, dear General so-and-so, that's a great thing to try to figure things out. And so they had no trouble breaking the encryption. The reason the message was thrown in the river was when the messenger arrived, it was July 4th, the Union had just taken Vicksburg and the Union flag was flying. So the courier threw the message in the river and went away. The decrypted message basically says, dear General Commanding, we regret to inform you, we have no troops to spare for the defense of Vicksburg, you're on your own. So turns out it wasn't really necessary to deliver the message. The situation had already changed. But there's a lot of fun stories like this. And these are great to share with students about how these can be used, how you could actually try to crack these using the techniques you know. Right. So let's go quickly to permutation ciphers. So this is hopefully going to be more secure. So why are we looking at nice linear functions? Really what we want is we want a function from the alphabet to the alphabet. And each letter goes to a distinct, that's what we said at the very beginning. Every letter goes to a different letter from every other. So there are going to be 26 choices for A. And this is why we want to allow sending A to A, because since we have 26 letters, maybe a few letters go to themselves and aren't shifted, but other letters are. It would be silly if every letter was sent back to itself, or if a huge number of letters were sent back to themselves. But in terms of the analysis, it's easier. So there's 26 choices for A, 25 choices for B, so on and so on. So we have 26 factorial. Anybody roughly know how big 26 factorial is? So it's a lot, but how big is a lot? So one thing is, we have for 26 factorial, we have all the numbers from 10 to 26. All of those, so that's at least 10 to the 16. The numbers from 20 to 26 all have a 2, so you have at least a 2 to the 6 from that. So just doing some quick calculations like this, you can see it's at least a decent size. What I actually like about 26 factorial is it's 4 times 10 to the 26. So if I just say, oh, it's around 10 to the 26, yes. But of course, 10 to the 30 is not of size 10 to the 30, 10 to the 100 is not of size 10 to the 100. This is a nice alignment. This is a lot more than the affine case. So earlier I was expressing confidence in this group. I know the extremely rigorous and detailed analysis that is done on all applicants. And I know that we have a group that is strong enough to break an affine cipher in half an hour. I am not confident about your ability, I apologize, to crack one of these by brute force analysis. Okay, so we have 10 to the 26. We divide this among 30 people.
Forget it.
So, it's well over 10 to the 24 possibilities for each one of you to try. So if we do brute force, it's secure. There's no way we are going to crack this by just pure brute force. So one of the real dangers in cryptography is you might have something that is really good from one point of view, but there could be a backdoor, there could be another way of attacking it. And the way of attacking this, as has been remarked, is frequency analysis. And your different letters and different alphabets will have different frequencies. These, the frequencies of English text from 9,481 English works from Project Gutenberg. And what a shock. E is coming in as the most common letter. Z not doing so well at 0.08%. All the way at the bottom. Q is a little bit better. So if you use one of these permutation ciphers, whatever letter occurs the most often, probably an E. What else could you do in addition to looking at just frequencies of letters? If you have a long text, what else do you expect to see? I'm sorry? What blocks? Yeah, 2 pairings or 3 pairings. So you can look at most common bigrams or most common trigrams. And so if I see a trigram occurring many, many times, likely it's maybe a the or an and or something like that. Anybody familiar with Bob Newhart's comedy? He has a great routine on monkeys on typewriters. And so you may have heard that if you give an infinite number of monkeys an infinite amount of time on an infinite number of typewriters, eventually one of them will bat out the complete works of William Shakespeare. And there's a great Simpsons routine where Professor Burns, I'm not Professor Burns, I've been in academia too long, Mr. Burns is trying to implement this, and he actually has a room of monkeys at the typewriters. And they're not doing Shakespeare, they're doing Dickens. He goes, it was the best of times, it was the blood of time. Starts yelling at the monkey. You actually don't need infinitely many monkeys. Finite number will do. But it will take a long time, if they're just typing away. So a lot of people have said, what can we do to help the monkeys? These are the same people who, I think, decided how to get rid of the seeds in watermelons. They were very concerned about these poor monkeys on typewriters spending all of eternity. So they said, let's help the monkey. So after we take the monkeys and start having them typing, the 0th order monkey just gets a regular keyboard and just bats away at all the keys, and we'll say every key is equally likely to be hit. Then we will have the 1st order monkey. So after you hit the keyboard, let's say I hit an H, I give the monkey a special keyboard that's a little bit larger, and it has the letters occurring with the correct frequency to follow the letter H in the English text. And then let's say the monkey hits a W. I'm not sure too many words begin with HW, but then the monkey would get a keyboard with the correct letter frequency following the W. And that would be the 1st order monkey. You could then do the 2nd order monkey, where you look at the last 2 letters hit and give the monkey the keyboard that has the right letter frequencies for that. If you do a little searching on the internet, you can actually find the Edgar Allan Poe monkey, the William Shakespeare monkey. I'm sure they have Janet Steele monkeys. You can feed in different texts, and the monkeys will write in the style by the time you get to, I think, a 4th or a 5th order monkey.
Maybe this is a good point to introduce general tendency of merging between computer science, math, and other disciplines, in this case, linguistics.
Right, and if you can...
Your examples are mostly related to English text.
Right.
But your enemies are not
correct
English
correct
speaking individuals. In German, they have other statistical distributions.
Yes, yes.
In Italy, Italian, or also other Russian 33 characters.
Right.
Which is absolutely different. And some even stroke-based languages like Chinese.
Right. And again, if I were to implement one of these, I would add some additional characters. So in English, I could have 2 different letters or 2 different symbols being the E. If anybody's familiar with Prince, who changed his name to the artist formerly known as Prince with a symbol, I would add a couple of extra symbols to go to E to try to adjust the frequencies. And then I would have some freedom in terms of how I spell. So there are things you can do to try to make this a little bit better. But this is very susceptible to frequency analysis. If students can do basic coding, they can actually write some code to simulate these monkeys with what is the right letter frequencies. And it becomes a really nice coding project. I actually had a student do this for a colloquium he had to give to graduate from the Williams Math Department. Okay, so we've got a few more minutes for the first session. So I want to talk a little bit about why do we use primes for encryption. So let's imagine P and Q are 200-digit primes. I'll multiply them and I'll get a large 400-digit number. And the password is P or Q. So if you give me any factor of n, I'll let you in. Or another possible password system is I choose a 5,000-digit random number, and the password is that 5,000 random digit number, and I give you no clues. So which do you think is going to be harder to guess? The 5,000 random digit number where I give you no clues, or a 200-digit divisor of n, and I tell you what n is. And there are 2 of them that work. So you only have to get 200 digits right versus 5,000. Which do you think is more security? The first one, which is only 200 digits, that's more secure than 5,000? I even tell you the number it divides, just factor n. Okay, turns out factoring is believed to be extremely hard. It's believed to be extremely hard because anybody who has publicly worked on it has said they don't know how to do it. It is possible that somebody has a good way to factor numbers and has not said anything. There's a wonderful movie, Sneakers, with an awesome all-star cast. that talks about what would happen if you could factor numbers quickly. But why would the 200-digit password be more secure than the 5,000? So some people have said 200. Why would that be more secure?
Because it's very difficult to find prime.
Yeah, right.
So forget that they're prime. Just try all 200-digit passwords. There are fewer 200-digit passwords than 5,000-digit passwords. How many 200-digit passwords are there? 10 to the 200. And 2 of them work. Whereas here it's a 5,000-digit password. There's 10 to the 5,000. So there's more passwords to try for the 5,000. Why are the primes better?
What was the question?
So why, I mean, I'm a number theorist. This is a cryptography lecture. Almost surely things involving primes have to be better than things not involving primes. So the first one should be the better way of doing things. But it seems like the second one should be a lot more secure. Any Monty Python fans here? No Monty Python fans? What's your favorite color? No, green. Oh. So if you've ever seen Monty Python, there's a beautiful scene where you have a gatekeeper and he's on the bridge and you have to answer his 3 questions to get past. How does the computer know that you give the correct answer in the second one? The computer says, give me your password. I say, okay, here's my password. Here's my 5,000-digit string. How does the computer know if you're right? It matches. The computer needs to know the password. If the computer needs to know the password, you have the opportunity to capture and torture the computer, or do the electronic equivalent of torture.
But it only matches the streets of zeros and ones, right? The computer doesn't talk any other language besides.
Well, but I mean, you can have it as, it doesn't matter if we're doing 5,000 0 and ones or 5,000 decimal digits. It doesn't really matter. In the second case, the computer needs to know the password. You have the opportunity to capture the computer and torture it and look at the innards. For the first one, does the computer need to know the password?
No.
No, it's, I'll know it when I hear it. So this is strange. You're hiring a security guard and you tell the security guard, only let in the good people, the appropriate people, the people who are on the list. Okay, who's on the list? Well, I'm not going to tell you that. Good luck with your job. It is, I will know it when I hear it. So the computer does not need to know the password. In fact, sometimes what happens is if you want to be extremely secure, you generate the primes P and Q on a non-networked computer and then smash the computers that were used to generate them and destroy them so that there is no record of any computation being done. And now the only way you can get in is to put in the 2 passwords. It is either P or Q, one of those 2 passwords. So the point is, if you try things by brute force, the second method is more secure. But 10 to the 200 is such a large number, if you try things by brute force, it doesn't really matter. So let's put things in perspective. So let's say every atom in the universe, and I'm pretty sure the Dymax budget will not allow us to do this, but we'll dream big. Every atom in the universe is a universe. And every atom in that universe of universes is a supercomputer devoted exclusively to our use, running since the dawn of time. And we'll say it can check 10 to the 15 items per second. That's more than I think the supercomputers can do, but think big. So there's about 3.2 times 10 to the 7 seconds in a year. So we could check about 3.2 times 10 to the 182 per year. Universe is about 15 billion years old. I know it looks only like 14 billion, but it's really about 15 billion. So in the life of the universe, we'd be able to check about 5 times 10 to the 192. We need to get up to 10 to the 200 for numbers to check. Or if you know that not every number is prime, if you have an efficient way to just enumerate primes, you'd still be around 10 to the 197, 10 to 198. So to put things in perspective, this is not enough to do a brute force check with every atom in the universe, a universe, and every atom in that universe, a supercomputer running since the dawn of time. That's not enough to crack this by brute force. So this gives you some idea of the level of security primes could potentially provide. We saw with the permutation cipher that if you use a frequency analysis, there is a way around it. And so the question is there a way around this factorization problem? If anybody can think of that, do not publicly tell anyone, talk to us privately afterwards. We will deal very carefully with the knowledge that somebody now knows how to factor large numbers carefully. Okay, so I think this is a good place to stop. It's been an hour. Does that sound good? Have a break now?
Yeah, we can take a break now.
Okay.
Restroom break, et
Okay.
cetera.
So I'm gonna.
Coffee break.
If you do need to take a restroom break, if you don't mind going around the loop to the right, they're working on a big signage piece in that hallway around the left. So it'll just be a little smoother.
So.
So go out of the room and turn right, and then wind your way around the loop to the restroom.
We're looking at you from the opposite side.